Hi students, now today we are going to talk about optical isomerism. This is very important concepts, right? Basically in optical isomerism, so what we are going to discuss, first let us observe subtopics in optical isomerism. Now combined problems in optical isomerism, problems on optical activity, resolution, racemic mixer, meso compounds, diastereomers, enantiomers, chiral other than carbon atoms. Okay, next one, molecules having pseudo chiral centers, calculation of stereoisomers, identification of chiral molecules, chirality, what is cause of optical activity, optical isomerism, RS, EZ, DL configuration, symmetry operations and molecular representations. Now nearly we have 18 to 20 topics in optical isomerism, but to understand all these concepts, even from symmetry operations onwards, symmetry operations, DL, EZ, RS, whatever the concept, now in optical isomerism, first we require molecular representations. With the help of these molecular representations, why? Because, for example, if you are going to compare in terms of what enantiomers, diastereomers, meso compounds, anything, so what kind of molecules you are selecting? You are selecting maybe either Fisher projections, Newman projections, Sahar's projections. Okay, so these are the different types of molecular models we are taking to understand the optical isomerism. That's why first I am going to start with these molecular representations, and interconversions. Now this is the basic and very important concept for optical isomerism, right? Now in molecular representations and interconversions, we have how many types of molecular representations? So in general, we have 5 different types of molecular representations. First, I am going to start with wedged as representation. Now, molecular representations, molecular representations. Okay, very important concept in molecular representations. Now, first one, wedge dash projection, wedge dash projection. That is our first molecular representation, wedge dash projection. And second one, Fisher projections, third one, Newman projections, right, Newman projections. And fourth one, Sahar's projections, and sometimes we are using zigzag representation, Okay, these are the 5 different types of molecular models. Once again, what are the 5 types? What is first one? Wedge dash projections. And what is second one? Fisher projections. Okay, third one, Newman projections, Sahar's projections, and next one, zigzag representation. First of all, so before going to discuss all these 5 different types of molecular representations, what is the use of these molecular representations? Okay, now in general we have 3-dimensional molecules. Okay, for example, if you are having 2-dimensional molecules, there is no need of these molecular representations. The best example, so if you are taking water molecule like H2O, what is hybridization of oxygen atom in this water molecule? Hybridization, sp3 hybridization. Even though that is sp3 hybridization, what is shape of the molecule? I am not going to discuss about the geometry. I am taking what is shape of the molecule. Now shape of this water molecule equals to what? What is the shape of the molecule? Bent, V shape or opposite to V shape, angular, whatever it may be. Okay, now bent molecule. Now here for example, if you are taking one imaginary plane like this, so all atoms exactly lying in the same plane. Once all atoms are present in the same plane, then that molecule is said to be planar molecule or non-planar molecule. That molecule is said to be planar molecule. Okay, so what is the meaning of planarity? Now once all atoms are coming into the same plane, then that molecule is said to be planar molecule. Okay, just you observe this one. Now this is our water molecule, right? Now here you assume oxygen atom, next hydrogen and hydrogen. Okay, for example, if your plane is passing like this. Now this is the imaginary plane. Once if you are sending imaginary plane like this through the oxygen atom and hydrogen atoms, your molecule is exactly divided into two equal parts. Otherwise, simply, if you are sending plane like this, all atoms are coming into the plane or not? All atoms are exactly coming into the same plane. If all atoms are coming into the same plane, then that molecule is said to be planar molecule, and simply we call it as two-dimensional molecule. So now this is two-dimensional molecule. So here our modern molecule is two-dimensional molecule. That is not three-dimensional, two-dimensional molecule. Two-dimensional molecule nothing but all atoms are lying in the same plane. For example, when you come to tetrahedral molecule, just like simple methane molecule I am selecting, okay. Around the carbon atom, how many bonds present in methane molecule? Now, methane molecule. This is our methane molecule, CH4. Who is the central atom? Carbon is the central atom. And how many hydrogen atoms present around the carbon atom? We have 4 hydrogen atoms around the carbon atom. What is hybridization of carbon? Here there is no lone pair of electron on the carbon atom. What is hybridization? sp3. And what is the geometry of this molecule? Here geometry of that molecule is tetrahedral. Okay, tetrahedral geometry. Now, for example, if you are trying to bring all atoms into the same plane, whatever the direction you are selecting, now just you observe this molecular model. This is our tetrahedral molecule. So whatever the direction you are sending, plane, okay. So whatever the direction you are sending the plane, all atoms not coming into the same plane. For example, if all atoms not coming into the same plane, then that molecule is said to be two-dimensional molecule or three-dimensional molecule. That molecule is said to be three-dimensional molecule. Okay. So whenever molecule is three-dimensional molecule, directly without any help, we cannot write that three-dimensional molecule on two-dimensional plane. That is the problem. Okay. So once again, there is no problem with two-dimensional molecules. So if you want to represent two-dimensional molecule on a plane, either horizontal plane or vertical plane, so there is no need of any theoretical rules, theoretical manipulations, and there is no need of molecular representations. But if your molecule is three-dimensional molecule, without any help and without any rules and regulations, we cannot convert that three-dimensional molecule onto the two-dimensional plane. Okay, so that's why now to convert three-dimensional molecules onto the two-dimensional plane, we are using these molecular representations. So now, what is the main important use of these molecular representations? Same point I am writing here, used to convert or used to write 3D molecules on two-dimensional plane, 2D plane. That is the main purpose of these molecular representations. Very, very important. These 5 molecular representations we are using to convert three-dimensional molecules on two-dimensional plane, or to write those three-dimensional molecules on two-dimensional plane. Okay, that is the main purpose. So we have how many types of molecular representations? We have wedge dash, Fisher, Newman, Sahars, and zigzag representations. Okay, now let us discuss one by one. First, I am going to start with wedge dash representation. Wedge dash representation or wedge dash projections. Wedge dash projections. So we know that these are the theoretical rules, theoretical manipulations. Now they are going to tell how to convert three-dimensional molecules onto the two-dimensional plane. Okay, clear. So what are the theoretical rules given by this wedge dash representation? Now here, according to wedge dash representation, to convert 3D molecules onto the two-dimensional plane, 4 different symbols are given. Okay, 4 different symbols. Now first one, this is what we call thick wedge. Next one, broken wedge, normal line, and wavy line. All these are very, very important. Okay, so totally how many different representations are given by wedge dash projections? We have 4 different types: thick wedge, broken wedge, normal line, and wavy line. So what is the main purpose of or main use of this wedge representation? First one I am going to take thick wedge. What is the meaning of thick wedge? Any atom or group which is present on thick wedge. any atom or group. Okay, once that is present on thick wedge, it indicates that that is nearer to observer, nearer to observer, nearer to observer, or above the plane, above the plane, above the plane, or front of plane, front of plane. Very, very important. Nearer to observer, nearer to observer, or above the plane or front of plane. So what is the meaning of above the plane or front of plane? For example, if your plane is horizontal plane and your atom or group is connecting like this. Now once your plane is horizontal plane, now this is looking like above or below? That is looking like above. So if your plane is horizontal plane, then we are using like above the plane, next one below the plane. Okay, for example, if your plane is vertical, plane is vertical, now we call it as front of plane or back of plane. Okay, just you look at this one. My plane is, if my plane is vertical plane, this one front of plane, next one back of plane. Okay, that is a way of using now these letters like nearer to observer, above the plane, next to front of plane. Similar to that one, if you are using broken wedge, for example, if you are using like broken wedge, what is the meaning of broken wedge? Broken wedge nothing but away from the observer, away from the observer, away from the observer, or second one below the plane or above the plane, this one below the plane, below the plane, below the plane, or back of plane, back of plane. All these you remember. Sometimes we are using above the, below the plane, sometimes we are using back of plane, like that when you are dealing with the molecules. Okay, back of plane, one and all same, away from the observer or below the plane or back of plane. Okay, that is the meaning of broken wedge. And what is the meaning of normal line? For example, if any any atom is present on normal line, atom or group, that indicates in plane arrangement, in plane arrangement. And what about the wavy line? Wavy line nothing but stereochemistry is not fixed, stereochemistry not fixed, nothing but that may be above the plane or below the plane. Here stereochemistry, stereochemistry is not fixed, stereochemistry is not fixed. That is the importance of four different symbols according to wedge dash representation. So once again come back to now this first one. Whenever atom or group is present on thick wedge, nearer to observer, above the plane, front of plane. Next one here, whenever something is present on broken wedge, okay, what is the meaning? Away from the observer, below the plane, back of plane. If something is connected to normal line, so what is the meaning? In plane arrangement. If something is present on wavy line, this is what we call wavy line. So whenever something is present on wavy line, simply we call it as stereochemistry is not fixed. Okay, now these are the four different symbols. Now with the help of these symbols, how we are converting that 3D molecule onto the two-dimensional plane. First I am going to take simple example, that is methane. How many hydrogen atoms present on carbon atom? 4 hydrogen atoms are there. First of all, your molecule is 3D molecule or 2D molecule. Your molecule is 3-dimensional molecule. Okay. Now, with the help of wedge dash projections, I am trying to convert that tetrahedral molecule, 3-dimensional molecule, onto the 2-dimensional plane. Now, this is our methane molecule. Here, how many central atoms are there? Only one central atom, that I am taking here, carbon, right? For example, if direction of plane is like this, just I am trying to send plane like this. So according to this plane, how many bonds? For example, if you observe from your side, now these two bonds either nearer to observer or away from the observer. For example, if you are the observer, how many bonds nearer to observer? Two bonds are nearer to observer. And these two bonds are nearer to observer or away from the observer. From your side, these two bonds are away and these two bonds are nearer. So two bonds are nearer to observer and two bonds are away from the observer. right? Now horizontal bonds are nearer to observer. These two horizontal bonds are nearer to observer. Same thing I am writing here by using what? Thick wedge. What is the meaning of thick wedge? If anything is present on thick wedge, that indicates nearer to observer. Two bonds are nearer to observer. Next one, these two bonds are away from the observer. Now we can write like this: two bonds are away from the observer. With the help of broken wedge, we can write like this: out of four bonds, two bonds are nearer to observer and two bonds are away from the observer. Okay, now here I am going to write these atoms like hydrogen, hydrogen, hydrogen and hydrogen. Asymmetric center is not required. Any molecule we can convert with the help of these molecular representations. Okay, just we are trying to convert 3D molecule onto the two-dimensional plane. For example, if you are having two carbon atoms just like ethane molecule C and C, hydrogen, hydrogen and hydrogen, 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 again here hydrogen. We have how many carbon atoms? Two carbon atoms are there. Okay, just you assume like this. Now this is our upper carbon atom. Again here also one carbon atom is present and bonds are connecting like this. Okay, now, for example, if you are sending plane like this is our imaginary plane. That CC bond coming into the same plane. So, whatever the, one second. Okay, this is our ethane molecule, right? Yeah. This is our upper carbon atom next to lower carbon atom. Fine. I am sending plane like this. So when this plane is my imaginary plane, this chemical bond is in plane or out of plane? That is in plane. That's why simply I am taking like this carbon and this CC bond is what coming into the same plane. That CC bond is lying in the plane. Okay, right. Next after that, come to upper carbon atom. At upper carbon atom, from your side, how many bonds are nearer to observer? Two bonds are nearer to observer. At lower carbon atom, two bonds are nearer to observer. Same thing I am going to represent here. At upper carbon atom, two bonds are nearer to observer. Horizontal atoms or groups. Here also same thing. These two are what? Nearer to observer. And here at upper carbon atom, this bond, this one, again this one, away from the observer. So we can write like this: away from the observer. Two bonds are there. One second. Yeah, two bonds are away from the observer. Okay, that is the way of converting two-dimensional molecule onto the, sorry, three-dimensional molecule onto the two-dimensional plane. So rest of the things are hydrogen, 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 hydrogen and hydrogen. Okay, what is the other way of representation? So once again, come back to same tetrahedral molecule, methane molecule, CH4, hydrogen, 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 hydrogen. Any direction you can use. For example, this is my plane. So that plane is passing through. Carefully observe this molecule. Now this is our real molecule. This is my plane. Carbon and two bonds are coming into the same plane. If my plane is like this, carbon and two hydrogen atoms are in the same plane. Next one, how many bonds nearer to observer? One bond is nearer to observer, one bond is away from the observer. So you can also write like this. Now here, how many bonds are in plane? Two bonds are in plane. Same thing I am taking here like hydrogen and hydrogen. And how many bonds are out of plane? Two bonds are out of plane. One bond is nearer to observer. Next one bond is away from the observer. One hydrogen atom is away from the observer. Okay. So once again, how many bonds are in plane? Two bonds are in plane and two bonds are out of plane. So out of two bonds, one is nearer to observer, one is away from the observer. Okay, that is the way of converting 3D molecule onto the two-dimensional plane according to wedge representation. Next one, for example, if you are going to Fisher projections, second one, Fisher projections. Second molecular representation, Fisher projections. Here lot of points are there, very important, right? Fisher projections. So in Fisher projections, how we are looking the molecule, that is also very important. So in all molecular representations, how you are looking the molecule, very important thing. Now in case of Fisher projections, we are looking this molecule in vertical fashion. Whenever if you want to write 3D molecule on two-dimensional plane in Fisher projections, you look at this molecule in vertical fashion. Okay. Now in case of Newman, same molecule we are looking along the CC bond axis. But in case of Sahars, this is a way of looking that molecule in diagonal fashion, upper diagonal and lower diagonal. Okay. Now come back to same Fisher projections. How we are looking that molecule in vertical fashion. So whenever you are looking this molecule in vertical fashion, you can see upper carbon as well as lower carbon atom. Not only two carbon atoms, even though there are 100 carbon atoms, all 100 carbon atoms you can see, right? All the carbon atoms you can see in Fisher projections. So what are the theoretical rules given by Fisher projection? First point I am writing like this. Point number 1, we are using one vertical line and one or more than one horizontal lines. This is the first theoretical manipulation given by Fisher. What is the first point? So whatever the molecule given, very simple, just after 3 to 4 points I am going to give examples. Okay, according to Fisher projection, what is the first point? Whatever the number of carbon atoms present, so how many vertical lines we are using? We are using one vertical line and one or more horizontal lines. Then you can represent like this. Now one vertical line and one or more horizontal lines. Here I am taking like this, one horizontal line. Otherwise one vertical line, one or more horizontal lines, nothing but you can use two horizontal lines, three horizontal lines, any number of horizontal lines, but only one vertical line. So that's depending on the given molecule. Okay, so here every cross is indicating carbon atom. Every cross is indicating carbon. Okay, very important point. Every cross indicating carbon. Clear? Here one vertical, two horizontal, next one vertical, three horizontal, like that. That is our first point. What is the first point? We are using one vertical line and one or more horizontal lines. And what is the second important point? According to this second point, here maximum number of carbon atoms. Maximum number of carbon atoms. Maximum number of carbon atoms should be on the vertical line. Maximum number of carbon atoms should be on the vertical line. Okay, that is the second important point. Maximum number of carbon atoms should be on the vertical line. And what is the third important point? Okay, maximum number of carbon atoms we are keeping on the vertical line, right? For example, if there is a competition between two groups, here this point is very important. More oxidizable group, very important point. More oxidizable group should be taken on top of the vertical line. More oxidizable group should be taken on the top of the vertical line. Very important point. More oxidizable group should be taken on the top of the vertical line. Taken on the top of the vertical line. That is the third important point. Okay, right. What is the meaning of more oxidizable group? More oxidizable group, nothing but you write this point, more oxidizable group. More oxidizable group, nothing but it contains more number of oxygen atoms. O stands for oxygen atoms, and less number of hydrogen atoms. That is the meaning of more oxidizable group. Okay, right. What is the meaning of more oxidizable group? It contains more number of oxygen atoms and less number of hydrogen atoms. For example, if I am giving like this carboxylic acid COOH and CHO. For example, competition given between CHO and CH2OH or COOH and CH2OH. Okay. Now these are the groups given. Now you want to arrange these groups on the vertical line, but which one we are taking on the top of the vertical line? According to Fisher projections, which one we are taking on the top of the vertical line? More oxidizable group should be taken on the top of the vertical line. How we can identify more oxidizable group? It contains more number of oxygen atoms and less number of hydrogen atoms. Now in carboxylic acid, how many oxygen atoms are there? Two oxygen atoms. Here one oxygen atom, which is more oxidizable group. Carboxylic acid is more oxidizable group. And come to this one, number of oxygen atoms are same. Then you go for number of hydrogen atoms. If group contains less number of hydrogen atoms, that should be taken as more oxidizable group. Okay, right. Here two oxygen atoms, one oxygen atom, which is more oxidizable group. COOH, carboxylic acid is more oxidizable group when compared to what? CH2OH. That is the way of identification of more oxidizable group. Clear? Fine. Come to next rule, another important rule. Now next rule says that, for example, this is our Fisher projection. I am taking here two horizontal lines. Okay, here which is eclipsing and what are the bond angles, that is also very important. So in general, for example, if I are taking like this A and B, according to this board representation, so what is the angle between A and B? So generally we can say that 180 degrees bond angle. Okay, here also almost in Fisher projection, if you are taking molecule like this, one vertical line and two horizontal lines, here I am taking like this, just like A and here B, A and B, right side something like X, Y, and here I am taking like P and Q. Okay, P and Q. So what is the angle between A and B, X, Y and PQ? That is very important. Once again come back to same molecular model. Only from the molecular model we can understand the bond angle between the two groups. For example, directly by looking at this molecule, if anyone is asking what about the bond angles, in general we say that between A and B what is the bond angle? 180 degrees, and between X and Y 0, and P and Q 0. Why? Because these two are what? Parallel to each other. Now these two are looking like opposite direction, but in the real molecule A and B not in the opposite direction. Now carefully observe this molecular model. Okay, so according to this molecular model, at upper carbon atom and lower carbon atom, mainly you observe this one as well as this one. What is bond angle between these two? These two are parallel to each other in the real molecule. Okay, this is our top group or top atom, and this one bottom, top bottom. Okay, what is the angle between top and bottom? Always 0 degrees. Now come to these points, very important. These 3 points are very important. What is the first point? Between top and bottom, between top and bottom, what is the bond angle? Bond angle equals to 0 degrees. That means top and bottom groups are eclipsing together. Now according to this Fisher, which one eclipsing to each other? One second. Yeah. So which one eclipsing according to this Fisher? A and B eclipsing together. Eclipsing together. What is the meaning of eclipsing? Eclipsing nothing but one is exactly back of other. Okay, and bond angle is 0 degrees. Now here between these two, what is the bond angle? 0 degrees. Okay, so A and B are eclipsing together. Next one, what is the bond angle between X and Y? Bond angle between X and Y. What is the bond angle? 0 degrees. Next one, between P and Q also 0 degrees. Between X and Y 0, between P and Q 0, between A and B also what is the bond angle? 0 degrees according to the real molecule. Okay, right. So XY eclipsing together, PQ and eclipsing together. So we can generalize that point. Now simply we can write like this: always top and bottom groups are eclipsing. Top and bottom groups are eclipsing. Eclipsing nothing but what is the bond angle? 0 degrees. Come to second point. All all horizontal groups are eclipsing. All horizontal groups are eclipsing. Okay. Otherwise we can write like this: all right side, one second, all right side groups are eclipsing. All right side groups are eclipsing. Next, all left side groups are eclipsing. These are the three important points. Okay. Top and bottom groups are eclipsing. All right side groups are eclipsing. All left side groups are eclipsing. Okay. These are the theoretical manipulations given by Fisher. Once again, come back to all these points one by one. Then we will go for examples. What is the first point given? Whatever the molecule given, what we are using? One vertical and one or more horizontal lines. One or more horizontal lines. Okay. What is the second point? Whatever the given molecule, maximum number of carbon atoms should be taken on the vertical line. Okay. And what is the third point? More oxidizable group should be taken on the top of the vertical line. This is the way in identification of more oxidizable group. Group which contains more number of oxygen atoms and less number of hydrogen atoms. Okay. Next point. What about the bond angles? Always top and bottom groups are eclipsing. All right side groups are eclipsing. All left side groups are eclipsing. Right. Now come to one important example. Now just to convert this molecule onto the two-dimensional plane. CH2OH, CHOH, COOH. This is the given molecule. By using Fisher rules, convert that molecule onto the two-dimensional plane. So how to convert this molecule according to Fisher? Yeah. First of all, here I am taking like this. How many carbon atoms present? 3 carbon atoms are there. First carbon, otherwise you can take from right side. First carbon, second carbon and third carbon atom. 3 carbon atoms are there. What is the first point? First of all, here 3 carbon atoms are there. All these 3 carbon atoms we are trying to arrange on the vertical line according to the Fisher rule. Maximum number of carbon atoms should be taken on the vertical line. Okay, right. Here one asymmetric center is present. Just I am taking only one horizontal line. According to 3 carbon atoms, even though we are not having idea about the asymmetric center, no problem. 3 carbon atoms are there. Now we know that minimum one horizontal line is required according to Fisher. Here upper carbon and this is the middle carbon next to lower carbon atom. Every cross is indicating what? Carbon atom. So according to that given molecule, 3 carbon atoms I am taking on the vertical line. Next one. Which one we are taking on the top of the vertical line? We have competition between COOH and CH2OH. Which is more oxidizable group? COOH is more oxidizable group when compared to CH2OH. Yes, that COOH I am writing here. Next one, CH2OH at the bottom of the vertical line. Then what about remaining two? Actually here you can expand this molecule like this. Now CH2OH, now OH and hydrogen. Next COOH. After writing COOH and CH2OH, what are the remaining? H and OH are left. There is no restriction on H and OH. Let me take one more molecule. Then after that we arrange H and OH. Here I am taking COOH. Next CH2OH. Right? After writing these two, then what about H and OH? According to your wish, you can take H and OH. For example, if you want to take OH right side, yes, you can take no problem, and left side hydrogen. For example, if you are going to take OH left side, then you take hydrogen right side. Okay, that is the way of writing Fisher projections according to the given molecule, right? Now this is the first example. Let me go for second example. Now this is our second molecule. Here I am taking like this, CHO. Next one, CHOH. This hydrogen atom completely I am writing like this. Okay, for 2-3 molecules, and COOH is given. So how we are writing that molecule in the form of Fisher? So here I am taking one vertical and one horizontal line. That indicates how many carbon atoms? 1, 2 and 3 carbon atoms. Here also same thing, 1, 2 and 3 carbon atoms are there. You can take numbering like this, 1, 2 and 3. 3 carbon atoms. I am not going for IUPAC, just I am selecting number of carbon atoms in the given molecule. Okay, right. After writing one vertical and one horizontal line, then go for extremely right side group and extremely left side group. So we have carboxylic acid one side, aldehyde other side. Which is more oxidizable group? No doubt carboxylic acid is more oxidizable group when compared to CHO. Why? Because your carboxylic acid contains more number of oxygen atoms when compared to aldehyde. So what we are taking on the top of the vertical line? On the top of the vertical line we are taking COOH and bottom CHO. Same thing you repeat in the same molecule, COOH and CHO. Clear? Then what about H and OH? Now as your wish. One time take OH right side, one time now we are taking OH left side, and fourth valency hydrogen. Okay, that is a way of writing now Fisher projections. Now come to one more simple example, COOH, C and COOH. Here OH given, again here also OH given, hydrogen and hydrogen. For example, this is the given molecule. Okay, right. First of all, you select the total number of carbon atoms, 1, 2, 3 and 4. From any side you can write the numbering, that is not about problem. Okay, this is the given molecule. We are selecting number of carbon atoms. Totally how many carbon atoms are there? 4 carbon atoms. So by default, if you are taking one vertical line, exactly at top position how many carbons present? 1 carbon. Next one, here also 1 carbon atom. Like that, here carbon and carbon, 2 carbon atoms are completed. And extra we require how many carbon atoms? We require 2 carbon atoms. For 2 carbon atoms I am selecting 2 horizontal lines. Okay, like this, 2 horizontal lines, and one more molecule I am taking like this. Clear? Next, after that, which is more oxidizable group? Now just you look at extremely right side group and extremely left side group. Both are similar. That's why here there is no competition. Now simply you can write like this, COOH and COOH. Here also same thing, COOH and COOH. Come to this one, COOH and COOH. Clear? Next, what about substitution at other carbon atoms? Here we have H and OH, again here H and OH, OH, H, OH and H. For example, if you are taking 2 OH groups right side, then by default left side hydrogen atoms are there. For example, if you want to take 1 OH here right side, 1 OH left side, then remaining hydrogen atoms are there. And even sometimes you can take here OH left side, here OH right side, and remaining hydrogen atoms. There is no problem at other centers. The mainly we follow at top of the vertical line which one is present. On the top of the vertical line, according to Fisher projections, more oxidizable group should be placed on the top of the vertical line. That is known as golden Fisher form. Okay, na? Now this is what about Fisher projections. Come to next one, Newman projections. Newman projections. Third important molecular representation, Newman. So according to Newman, okay, according to Newman projection, how we are writing 3-dimensional molecule on 2-dimensional plane. Yeah, come back to this molecule. For example, if you are looking this molecule in vertical fashion, that is fission. Same molecule if you are looking along the CC bond axis, that is Newman. Okay, if you are looking this molecule along the CC bond axis, that should be taken as what? Newman. Clear. But what is the problem in Newman? For example, if you are looking this molecule along the CC bond axis, now this is your front carbon atom and this one back carbon atom. Okay, front carbon and back carbon. Once again, you look at this molecule. This is the way of looking that molecule, front carbon and back carbon atom. What is the size of both carbon atoms? Both carbon atoms size is exactly identical. According to Newman, if you are looking this molecule along the CC bond axis, because of identical size, you can see only front carbon atom and you cannot see back carbon atom because of identical size. Okay, that's why here, according to Newman, in order to see both carbon atoms, now rules are given like this: front carbon atom represented by dot, front carbon atom represented by dot, and back carbon atom represented by circle. That is the theoretical rule given by Newman. Very important point. According to Newman projection, whenever you are looking this molecule along the CC bond axis, okay, you can see only one carbon, front carbon, and you cannot see that back carbon atom. But if you want to see both carbon atoms, just now you take carbon atoms like this, front carbon atom dot and back carbon atom circle. It doesn't mean that both are having different sizes. That is not the meaning. Just in order to see both carbon atoms, one carbon atom we are taking as dot and one carbon atom circle. Okay, that dot is taken as front carbon atom. Clear? Now this one front carbon atom. And what about circle? Now this is circle, nothing but back carbon atom. That is the difference. Okay, front carbon atom and back carbon atom, right? So after selection of front and back carbon atoms, next important thing, how the groups or atoms or bonds are separated by how much angle. Okay, so at front and back carbon atoms, okay, let me write one by one. First point, what is the first point? According to Newman, front carbon atom represented by front carbon atom represented by dot. Represented by dot. Clear? And what about back carbon atom? Back carbon atom represented by circle. Back carbon atom represented by circle. These are the 2 points. Front carbon atom represented by dot and back carbon atom represented by circle. Next, another important point. Okay, at front and back carbon atoms, any two bonds are separated by 120 degrees angle. Any two bonds are separated by 120 degrees angle. Okay, now these are the theoretical rules given by Newman. What is the first point? Front carbon atom represented by dot, back carbon atom represented by circle. And what is the bond angle between any two bonds at any carbon atom? At front carbon as well as back carbon atom, any two bonds are separated by 120 degrees angle. Okay, for example, if you want to write by using what Newman, let it is front carbon, next this one back carbon atom. Different varieties are there. I am going to take first like this. Yeah. And what is the arrangement of atoms or groups? Here arrangement of atoms are like this. You observe that one between any two bonds, what is the bond angle? 120, 120 as well as 120. Next one on back carbon atom, you can take like this, back carbon atom, yellow, next one here also yellow, next yellow. Okay, at back carbon atom also, what is the bond angle between these two? 120 degrees bond angle. At front and back carbon atoms, bonds are separated by, okay, one second, bonds are separated by 120 degrees. Yeah, first I am taking at front carbon atom, down side, right side and left side with 120 degrees bond angle separation. Next one here like this at back carbon atom. Okay, now same bonds we can also write like this. One is up, left, next one right side. Next at back carbon atom you can represent like this. Okay, so what is the meaning of this representation? Here between these two bonds 0 degrees. Once between two bonds 0 degrees bond angle present, at everywhere you observe same angle 0 degrees. Okay, like that here also what is the bond angle? 0 degrees. Next one 0 degrees. Next here also 0 degrees. I am not going to give any kind of nomenclature like eclipsed form, staggered form, like that we will see later. Now this is the way of representation. For example, if you are going to take like this, front carbon atom dot, next back carbon atom circle. Okay, front carbon, next again back carbon atom. At front carbon atom, I am taking groups like this. Again, what is the bond angle? 120 degrees bond angle. Next at back carbon atom, you can also write like this. Here also same thing, 120 degrees between two yellow, 120, again here also 120. And sometimes they can give like this, between any two bonds 120 degrees bond angle separation, at a back carbon atom also 120. Okay, these are the four different ways of representing Newman's projections. Again these two, right? Come to next theoretical molecular representation, that is Sahar's projections. Sahar's very simple. What is the difference when compared to what Fisher? Now according to Sahar's, you look at this molecule in diagonal fashion. Now this is the upper diagonal and this one lower diagonal. Okay, so in case of Sahar's, you can see both carbon atoms, upper diagonal as well as lower diagonal. Okay, simply you can write like this, diagonal. Next one, at lower diagonal, now bonds are separated by how much angle? 120 degrees. Upper diagonal also same thing, 120 degrees. Now between these two 120, again 120, between these two 120. Okay, that is the Sahar's representation. Now simply remember like this, even sometimes the molecules they are giving like this by using what horizontal line. So how to arrange groups at each carbon atoms according to Sahar's? Yeah. So according to these Sahar's, just we represent like this, below and below. Two bonds you write below. Next one, two bonds above. At both carbon atoms we are taking two bonds above. And one is above, one is below. Next one here, below and above. Below and above. Okay. Next, what about the arrangement of other bonds? Just you write in the form of Y. Y. Again here also Y. Clear? Next one here, again Y form, like this. Next one here, like this and like this. Here also same thing, like this. Okay, these are the different forms of Newman. Yeah. Last one, zigzag representation. According to zigzag representation, in zigzag representation, let us take one reference line like this. This is our reference line. Okay. According to this reference line, one carbon atom is below that reference line, one carbon atom above, below, above, below, above. Just you connect like this. This is what we call zigzag representation. That's it. So what is the meaning of zigzag? With respect to your reference line, okay, straight line, one carbon atom above, one carbon atom below. That is what we call zigzag representation. Sometimes now you can see molecules like this. Now this is what we call zigzag representation, and they are giving arrangement like this, like OH, and here something like OH, OH, or OH, like that according to wedge. For example, according to wedge, this one above the plane or below the plane, above the plane. Next one here above the plane, above the plane, and this one below the plane. Okay, these are the theoretical rules or theoretical manipulations. With the help of these, we are converting 3D molecules onto the two-dimensional plane. What are these? Wedge dash, second one Fisher, Newman, Sahars, and zigzag representation. Okay. Next we will discuss about what? Interconversions. How we convert wedge to Fisher and Fisher to Sahars, and even sometimes Newman to Sahars, Newman to Fisher, like that. These are the interconversions. Okay, right.